from node to node. It has a specific term. Conduction-wise. I'll give you conduction. There's another term up here. You ever heard of that term? Saltatory conduction?
Yeah.
Okay. These conductions, action potential is conducted down these nodes of Ranvier. Okay? So when you disrupt saltatory conduction, which is this down here, then that's going to affect the efficiency of the nervous system to get these electrical impulses to its effective order. Okay? Again, pretty much review from anatomy and physiology. Any questions so far? You gotta love the nervous system. So neurologists are some of the brightest people in the world. If you think about that, how smart that they have to be to all of the functions and things that the brain does that you guys don't think about. Think about your eye for a second. What does your eye do? Can you move your eye up and down? Yeah. Can you move your eye left and right? Okay. Can you move your eyes in circles? And while you're doing that, can you still see while you're doing that?
Yes.
What do you want me to see?
Whatever, can you see?
Yeah.
Some stuff.
Yes, some stuff, exactly. So just think about the complexity of the eye movements and controlling those with the brain, and then magnify it to the whole body. The brain is an amazing thing. And so that's why we are likely not, you and I probably won't see artificial intelligence in our lives because of the complexity of that. Now, can we control our garage door and our thermostats from home with our thing? Yeah. Is that intelligent design? Sure. But ultimately, that's not doing complex eye movements, moving your eyes so that you can foveate an object on the back of the retina so that you can see. Okay? And you take that for granted, right? How many people have vision corrected? We're in contacts right now.
Yeah.
You're good?
People like that.
So, how is it to walk around without your glasses on?
It's like underwater.
Yes.
I can't see anything.
Yeah.
I can't function. I have to stay home.
I can see things. Some things far away are a little blurry.
I'd be falling down, tripping
Oh.
over things.
Nuh-uh.
Yeah.
Really?
Mhm. So that's how bad. I wouldn't be able to see depth, like stairs. So I don't know what water looks like. That's got to be pretty bad, doesn't it?
You never open your eyes underwater?
No, no.
It's like, you should do it and then you know how
So you're pretty bad.
it's like,
You
yeah,
don't-
it's really blurry.
You don't open your eyes in the water when you swim?
But I have to believe that's pretty bad vision.
Yeah, it's my contact prescription's a negative 375.
Mine's 425, 475.
Jeez.
Wow, mine's 1.25.
Oh my god, I would kill for that type of vision. I can't function.
I would stay away from Lance's motorcycle if I was your kids on the
I know, oh my God.
End up killing
I
you.
thought mine was bad.
I think I know where it went wrong too. Like as a kid, you know they tell you, this is really stupid,
Eat your
okay?
carrots?
No, you know they tell you as a kid, like, don't look at the sun. I would like take that as a challenge. I would like have staring contests with the sun.
Oh my gosh. I met a lady at Sprouts
I'll be
one
like
day
6 years old, just like,
that did that.
I don't
That
see what the
does
problem
that.
is.
She calls it sun gazing. She says it's improved her vision. I call BS.
Yeah, your example is this right here. Ray Charles of the Exphysiology class would stare at the sun too long.
But it's been the same for like the last 3 years, so I think I'm good right where I am.
Yeah. Wait till it gets worse,
Yeah.
dude.
I want to wait for them to improve LASIK, and then I will go and swing for the
Swing
operation.
for that. That's awesome. So how do these impulses go from axon to axon? How do we transport them across? There are not one continuous network of electrical wiring in there. We have breaks in them, right? So we have these synapses, okay? And so what we're able to do is these impulses will travel down to the end of an axon where there's a synapse. These causing the release of chemicals or neurotransmitters that then will bind to receptors and then start the action potential over again in the next or connecting neuron, okay? So again, review, if we have an axon that's conducting a nerve impulse and impulse is traveling down here, it's going to get to this break or this synapse where it's going to cause a release of neurotransmitters from these synaptic vesicles, okay? They'll travel across this cleft and then bind to specific receptors for that neurotransmitter, basically then causing sodium-potassium channels to then open up and an action potential will be generated along that neuron, okay? So again, a complex system for us to allow the electrical impulse to travel from different sections of the nervous system, even to, we'll look at the neuromuscular junction where that electrical impulse is coming from a nerve to skeletal muscle. But if you look at this electron micrograph, I think this is always pretty exciting, okay? So you can see that this is that cleft or that void area that that neurotransmitter is going to come across. This would be the effector cell. In this case, it's a muscle fiber, okay? And we're looking at this, in this case, we're looking at the synapse here between the neurons. So this is the nerve right here, axon terminal right here. And you can see all these dark blue are what? Mitochondria. So what do you think about that when you think about mitochondria?
Oh.
Exactly. So it probably takes quite a bit of energy to produce this release of neurotransmitters, okay? And then each of these teal or blue-green dots is one of these vesicles with a neurotransmitter. In this case, if it was a muscle fiber, what would be the neurotransmitter? Acetylcholine, okay? So acetylcholine is in each side of those little bubbles, and then as they break, the vesicles release or dump acetylcholine into that cleft, and then they can bind on a muscle fiber, okay? But I think that electron micrograph is cool looking at those vesicles. I'd like to be able to shrink us down. Is it Ant-Man that can go really small? Is that the superhero?
Yeah.
To go look at those things? How awesome
And
would it be
Wasp.
to go look at all these things?
Magic, what is it, the Magic School Bus, or that cartoon?
Most overrated cartoon of all time.
What's it called?
I think it is the
Yes.
Magic School Bus.
Magic
Yeah.
School
Who's
Bus.
the woman on the Magic School Bus?
Frizzle.
Miss Frizzle!
Miss Frizzle, yeah.
That's out my children all the time. So, fantastic. Okay, same thing here. Different book, different look. You can take a look at it if you want to. Review again. Okay? So, do you remember this from Dr. Murphy's talk? Excitatory postsynaptic potentials, EPSP.
No.
How about inhibitory
Yes.
postsynaptic potentials?
Yes.
If you heard of inhibitory, how come you didn't hear about excitatory?
I don't remember the EPSP, but I remember the actual phrase.
Okay, so in this case, excitatory postsynaptic potentials are going to cause depolarization, but we can get summation. So when you're talking about summation, what are we talking about? Adding them up. That's exactly right. Okay, so basically what you're doing is adding things. Okay, so temporal summation is summing several EPSPs from one presynaptic neuron. Okay. And spatial summation is summing from several different presynaptic neurons, okay? So, in this case, this is multiple, this is multiple EPSPs from one neuron, and spatial is summing one ESP from several different neurons, okay? And we'll take a look at what that looks like, okay? So, here we have these EPSPs, okay? 3 excitatory neurons here fire. Their grade potentials separately are all below threshold. Okay? So they're releasing neurotransmitters across the cleft, binding to receptors in this other action or other neuron, and we generate this action potential. Okay? But the key here is they were all below threshold. But if you add them up, okay, create a super threshold signal, then the action potential is generated. If you got rid of one of these, the action potential would then not travel down this neuron because it may be below the threshold. But if you add all 3 of them together, what do you get? You get enough of a change or input that will cause the millivolts of the resting membrane potential to go above minus 55, and you get an action potential, okay? So which summation was this? Everybody agree with that? I'm just asking.
Mhm.
Let's go back and look at this figure right here. Does that change what you think now, Austin? Specifically, look over here. So that has 2 axon terminals, correct? But it's only 1 neuron, correct? Here's the neuron right here, right? So let's go back here to see what you said. Which one is that? Is that temporal
Wait.
summation or spatial summation?
It still looks like
Adding it
spatial.
together and- does it mean
It's
adding-
summation.
Is adding, does the temporal mean adding together inside one neuron from several different sources?
So temporal is summing several EPSPs from one presynaptic neuron, whereas spatial is summing one ESP from several different presynaptic neurons. So in this picture, is this temporal or spatial summation?
Spatial still.
It looks like spatial.
The answer is, you don't know.
'Cause we did-
Well, because you can't see the other end.
You don't know if it's coming from 1 neuron or 3 neurons, correct? So this would just show you what summation is, but it doesn't show you if it's temporal or spatial, because you can't see what's happening in that presynaptic axon terminals. If this were separate neurons, 1, 2, 3, what summation would we have? Spatial, okay? But we don't know what's going on with that. So this just shows you summation. It doesn't show you temporal or spatial summation, okay? Good. So is there always an answer? Sometimes there is.
There's
There's
always
always
an
an
answer.
answer.
There's always an
We have
answer.
enough information to come to that conclusion. That's what I like about textbooks. Textbooks, you guys say it is black and white. So Austin he's like, it's spatial. 3 of them, right? He
Yeah.
was quick with that, wasn't he? Why was he quick with that information?
Because it looks like 3 different neurons.
Yeah, exactly. That's what you don't know, okay? So here we are, this textbook, and this is a great textbook. This is one of my favorite textbooks, okay? So now, how do IPSPs fit into this, okay? So now we're talking about inhibitory postsynaptic potentials, which cause hyperpolarization. If you look at it here, same figure that we saw before, okay? 3 presynaptic axon terminals. But in this case, one of them is giving a negative or inhibitory signal, okay? So you have 2 of them that are providing a positive and one of them that's providing an inhibitory signal, okay? So the sum potentials are below threshold, so no action potential is generated. So because this negative one in here is dropping this to below minus 55 millivolts, we don't get an action potential there, okay? So this allows us to control action potentials within the nervous system, is we can have these EPSPs that are giving a positive stimulus or depolarization, but if we have inhibitory ones that are causing repolarization, it can decrease the amount or voltage of that stimulus, and it might be below what we need for the minimum threshold, and you don't get an action potential, okay? So this is going to become important when we talk about skeletal muscle. So remember EPSP and IPSP, okay? So here's more of this to see what happens with it, Okay, so blow this up a little bit here. We have postsynaptic inhibition. So in this case, we have an IPSP plus an EPSP, modifies the neuron signal, no response. Okay, so below the threshold. That's how that IPSP works. Okay, here in the presynaptic. So what was the difference between this one? So this is postsynaptic inhibition. Okay, why would it be postsynaptic inhibition?
Adding together inside the neuron, isn't that being a trigger?
So the key word here is postsynaptic inhibition. So where is it happening now? And what synapse are we talking about?
Synapse,
Right here, right? So if we blow that up, we're talking about this right here, right? So we have this postsynaptic inhibition, okay? Modifies the signal, we didn't get a response. 1 negative, 1 positive, 0, no response on target cells. Now let's take a look at this one. What's the difference here? Okay, so we have our excitatory neuron. Here's our neuron coming down here. Same thing with our effector organs, okay? Okay, and so we're getting neurotransmitter release from this synapse, neurotransmitter release from this synapse, okay? Causing an effector response, but look at the top one, what's happening there?
It's inhibiting.
So we have an inhibitory neuron that is affecting this right here, okay? So it's happening prior to the synapse here, okay? So in this case, this is presynaptic inhibition, okay? So all ways neural controls with these IPSPs that we can control these target responses to our effector cells, okay? We could actually do it here by affecting the action potential that travels down, which would be postsynaptic. And in this case, we're talking about the postsynaptic addition of an IPSP plus an EPSP. Here, we're talking about presynaptic inhibition at the level right below, before the target organ on that presynaptic axon terminal, okay? And so now this action potential is still traveling down, and we get obviously above the membrane potential threshold, and it's going to have a response at 2 of these, but this one giving us negative is going to have a lack of response, okay? So even though it's farther down, this is still called presynaptic inhibition because its reference is based upon what? The prior one is this. We're talking about this synapse here, and the other one we're talking about this synapse. So it's the relationship to what happens with where the IPSP is having an effect. Here it's after this synapse, so it's down here, okay, so that's postsynaptic. But here, in the next one, it's happening prior to this synapse, which would be presynaptic. Even though it's further down the chain, it's still presynaptic. Does that make sense? It's all your reference point. Questions on that? Anything? Again, a review of neurophysiology, okay? We haven't even talked about exercise, but all of these are going to be important with exercise, okay? So now we're going to get into the exercise part of things. So you're sitting here right now, is that correct? Do you know where your butt's at? Do you know where your feet are at? Do you know where your head's at? Okay? Do you know how you're writing on paper? How do you know that? Okay? So you're sending sensory information to the brain. What would happen if you didn't have that? If you didn't know where you were at spatially? That'd be problematic, wouldn't it? Okay? If you didn't know where you were at, okay, could you write paper? Oh, I didn't know where the paper was at. Or you're writing, but you don't know if you're touching the paper or not. Yeah, oh, I'm over here, but I'm looking over here, okay? So, and you think about that and how you guys do that every day. What if that was all fouled up? So think about walking. When you're walking, what kind of proprioception? Lance, you're a biomechanics guy. So what kind of proprioception is feeding back into walking? Or we're
Internal.
running for that math.
Center of gravity over your face.
you want to know what you're trying? Are you asking me about like the cellular level?
I'm asking you, could you walk without these sensory
Oh,
reflexes?
no.
No, not at all, could you? You don't know where your foot's at, how much pressure you're putting on it, you don't know where your knee's at, okay? How to move your knee in the proper orientation so that you can do that. Think about your stride that you have for your running stride. How does your body know that your one is in the relaxed or motion phase and one is not in the motion phase? Think about coordinating that now, okay? So think about when you were children, or when you've seen children lately. Have you ever watched them walk?
Yes.
Yeah, it's pretty interesting, isn't it? It's not smooth, is it?
No.
They're not like, hey, what's up? What do they usually do?
Bump into
It's like-
stuff.
And then what happens is they start going faster because they're out of balance. They're trying to stay upright. And they topple, right?
Yeah.
Okay? So what's happening is they're starting to use all these proprioceptors to realize where their body's located at in space. They have known it before, but they're not using it in the same way, okay? And so obviously we get better at it. But this is going to be key for us with exercise, human motion. These proprioceptors are going to provide information to the brain and spinal cord about where we're located position-wise, okay? Locations of our joints and muscles, okay? And kinesthesia is going to be this conscious recognition of the position of your body parts, okay? And how fast they're moving, right? So when you're walking to class, Hannah, you were sprinting to class. Did you know you were sprinting to class? Were you consciously aware of what you were doing when you were trying to get here on time so that you didn't get yelled at? Yeah, you did. So kinesthesia is going to be that conscious recognition of these sensory reflexes that are going on. Okay? So what kind of joint proprioceptors do we have? 3 nerve endings, okay? Push down on the table, you're sensitive to touch and pressure. Okay? So they're initially strong, but your butt went numb halfway through the class. Austin just had to go walk and get his butt, okay? At some point, they become adapted to that stimulus, and the stimulus isn't going to be treated as strongly, okay? So if you were to put your hand on a sharp pin, would there be quite a bit of pressure and touch on there on the pin? But could you keep it on there for a long period of time? Probably. Would that pain go away after a while? Ish. Not going to be as strong as it was, but it probably could adapt to that pain. So have you guys ever adapted to pain in the past?
Yes.
Give me an example. Marathon? What pain did you have, Austin?
All of it.
All of it? And so,
Oh,
how did you adapt to it?
Generous breathing, just keep going and eventually it subsides.
So you pushed the sensation back and just decided not to pay attention to it?
Essentially.
Could that be problematic?
Good.
Yeah. Could lead to what?
Shouldn't.
Injury, death, okay? Give me another example of something that you've adapted to pressure-wise or sensitive-wise.
Kind of going in your head.
Bright lights after your weekend in Vegas, right? Yeah. Been in the casino, they keep the lights down there, so they don't want you to know what time it is, your clocks and that stuff.
Maybe like
Heat.
heat.
So you're out in the heat, if you acclimate, it doesn't feel as bad.
Maybe it's like 110 outside. You get used to it.
You never get used to it, trust me.
What does acclimate mean?
Acclimate means that you're responding to environmental conditions and you're having a beneficial response that allows you to tolerate it better. So to acclimate, like if you were to talk about acclimate, we could do that in the environmental chamber where you would exercise over a period of 10 to 14 days. Your body would respond and show different physiological adaptations that would allow you to tolerate that heat better than when you started. So same thing as like 3-a-day football practices in August. Okay, what they're trying to do is get them to acclimate to that environmental stimulus so they can play in those kind of areas. Okay. So we're going to talk about these joint proprioceptors. Okay, specifically the 2 that we'll talk about are the muscle spindle and the Golgi tendon organ. Okay, but these are going to be important with regards to muscle. And now we're talking about muscle before we've actually talked about muscle, but it's important to understand that these are the neural aspects of this rather than actually skeletal muscle contraction, but it involves skeletal muscle contraction and our sensory feedback with regards to what we're seeing with them. Okay, so muscle spindle responds to changes in muscle length. Okay, and if you were to look at what this looks like, okay, So muscle spindles are located within parallel to muscle fibers, okay? So you can see, this is a muscle fiber here, 1 muscle fiber, 2 muscle fiber, 3 muscle fibers, 4 muscle fibers. So each muscle fiber going down, okay? Can't see that very well, maybe we should do a different pen color. Okay, 1, 2, 3, but it's located parallel to that. Now, within that, you're going to see the spindle. Here's the muscle spindle right here, okay? What's the first thing you notice about this muscle spindle?
Bulge.
It's what?
Bulge.
It's bulged. Now, I would look at the nerves. So look at that, it's highly innervated, right? Okay? So if you look at this, you can see there are either this dark blue or purple are gamma motor neurons, and then the green are sensory neurons. Why are those important? That's correct. So sensory, this is a spindle that is, we're supposed to be looking at, get this zoomed in, okay? To changes in muscle length, we're going to have sensory neurons that are going to allow us to get impulses back to the central nervous system, right? Okay? And so, and now, Austin said efferent, we have gamma motor neurons, okay? What is different about this gamma motor neuron? So first of all, what motor neuron contracts these muscle fibers? Is it a gamma motor neuron? Alpha motor neuron, okay? So alpha motor neurons contract skeletal muscle fibers, okay? Gamma motor neurons are going to contract these muscle spindles fibers. So there's different innervation for these spindles, okay? Because you don't want them contracting similarly with this, or you're not going to be able to detect changes in muscle length, right? And then the sensory or stretch that you see is going to be dictated by the input that's going back to the sensory neuron, okay? And so these are located in muscle bellies so that we get a indication of what's going on stretch-wise, okay? So muscle spindles detect the stretch of the muscle, okay? It's going to be here. Then sensory neurons conduct action potentials to the spinal cord, okay? Good. Sensory neurons are going to the spinal cord, okay? Spinal cord does what? We get a synapse with an alpha motor neuron. So there's our synapse right there, okay? What do you notice though? There's a break in there. Where's one goes to the alpha motor neuron, where's the other one go to? Brain, okay? Okay? And then the alpha motor neuron is, if you have stretch, what's going to happen? What's going to be the response? That's going to be exactly right. So the alpha motor neuron is going to be stimulated, okay? It causes the muscle to contract and resist stretch. So muscle spindles detect stretch, sensory neurons conduct the action potentials to the spinal cord, sensory neurons synapse with alpha motor neurons. Alpha motor neurons are stimulated, causing the muscle to contract, thereby resisting stretch. Okay? So, what kind of reflex is this? Does it have to go all the way up to the brain and then back down? No. So what kind of reflex is it? It is a spinal reflex. Okay? Why would we want this to be a spinal reflex? All of this happening right here in the spinal cord.
So isn't the travel is for?
Speed, right? So if we have to take this all the way up to the brain to initiate a response that comes back down to stimulate that alpha motor neuron, we could be stretching the muscle to the point of injury or no repair, okay? So this is going to be much faster. Spinal reflex is going to be much faster if it than going all the way up to the brain and then coming back down the brain, okay? When we're talking much faster, what are we talking about? Milliseconds here. We're not talking about, it's not going to go to the brain and hang out for like 5 minutes and then come back down, right? So it's going to be the difference. But the difference could be, in milliseconds, could be the difference between, let's say, contracting that muscle and causing no damage to causing maybe tear or severe damage to that skeletal muscle, okay? So when have you guys ever had your muscle fiber tested, or muscle spindle tested? Anybody know? The knee jerk is what Noah's telling us. Why would you say that?
Why did
First of all, tell us what the knee jerk reaction is, and when did you have it tested?
in the doctor's office, when they hit, what they hit, just a little tendon there.
Yeah. So what does that do?
I don't know really.
It has a sudden lengthening of the patella tendon.
Test your response.
Sure, nerves
How
are good.
does
Your
it work?
your nerve response.
Yeah. So that's what you're testing. Is you're testing that reflex, right?
Automatic stretch, because automatic contraction back to the body.
So how does it stretch? How does it stretch when you? Where are you placing what are you doing, Austin, with it?
Patellar tendon,
You're hitting the tendon with a hammer, right? And then what is the response that you're looking for?
response.
The contraction goes to basically contradict the lengthening that you're experiencing.
Okay. Okay. So what do you see when you do it? So you kick, right?
Mhm.
So, and you should have gone to your pediatrician. They should test that all the time, every time you had a physical. Didn't they? When's the last time you had a check?
Long time.
Long
Yeah.
time.
Laboratory last year.
Did
We
we?
went over
Did
this.
we?
Did we? As a lab, 100% that we did.
Hmm. Hmm. Wow. It's a little disappointing. And with that, we're just gonna shut this show down. Why don't we start back from zero, send you back down to anatomy and physiology. So what happens is you place a hammer, tap that patellar tendon, it stretches the tendon by indenting the tendon, initiates the muscle spindles, sensing stretch, follows this pathway, causing contraction, and you should see a kick out. Okay? If you don't, guess what? Maybe you didn't develop correctly, your reflexes aren't there, or maybe you're getting old.